Okay, let's talk about Euler's formula. Euler's formula uses the exponent function with a complex valued argument to represent an arbitrary complex number in polar form. And that's what I'm trying to illustrate here. I'm drawing a circle with a fixed radius. This circle is in the complex plane, where the x-axis is the real component of a complex number and the y-axis is the imaginary component of the complex number. Unfortunately, the imaginary axis label is clipped from this video. We can use basic trigonometry to determine the real and imaginary component of z. Here theta is the angle and a is the radius of the circle. The real component is a cosine theta and the imaginary component is a sine theta. Okay, so this is still pretty straightforward. So a complex number z has a real component x and an imaginary component y, and in polar form we can relate them to a cosine of theta and a sine of theta. So here comes Euler's formula. A times e to the power of I times theta is the same as a times cosine theta plus a times I times sine of theta. Now it's actually pretty easy to prove this formula using a Taylor series expansion of the exponent function and the cosine and sine functions. You can go and prove this for yourself if you're interested. And that's how we can relate an exponent function, a cosine and sine function, and a Cartesian representation of a complex number together. Complex conjugation is an often used operation for complex numbers. Conjugation is often represented using a superscript star, and it means just flipping the sign of the imaginary component of the complex number. This diagram represents z and z star, its complex conjugate, which is just a mirror image of z mirrored around the real axis. In complex exponent form, conjugation means flipping the sign of the angle theta. You can use the complex conjugate to obtain the real or the imaginary component of a complex number. I'll show you how to get the imaginary component. I'm sure that you can then figure out how to obtain the real component. Using 1 divided by 2i times z minus z conjugate, you obtain the imaginary component of a complex number z. And we're going to use Euler's formula to prove that. The reason why we're using Euler's formula in this case is because it will allow you to see the relationship between a sine function and the complex exponent function. Okay, in the interest of time, I'm going to speed this up a little bit. And here's the results. One often used application of Euler's formula is to relate a cosine function to two complex exponential functions. So cosine is the same thing as half times e to I theta plus e to minus I theta. And what is e to I theta? It is just a complex number which has an absolute value of 1, and e to minus I theta is its conjugate. Similarly, we can relate the sine function to the complex exponent function. 1 over 2i times e to I theta minus e to minus I theta is the same thing as sine of theta. I'm going to show you an example of a situation where the complex exponent function representation of a cosine and sine is very handy. If we multiply a cosine and a sine signal together, what do we get? In this case, the cosine signal has an angular frequency of omega 1 and the sine signal has an angular frequency of omega 2. This type of an operation is commonly encountered in radio engineering, in radio signal processing. It is used to shift signals up and down in frequency. Radio engineers call this operation up conversion or down conversion. To proceed, we are going to write the cosine and sine functions using complex exponent functions. Here's the complex exponent function representation of the cosine and a sinusoid. Now, because complex exponent functions are really easy to calculate with, all we need to do is a bunch of algebraic manipulations to see what we get. Okay, so what do we get? We get one sinusoid with frequency omega 1 plus omega 2, and another sinusoid with frequency omega 1 minus omega 2. Now let's draw a spectral representation of what's going on. I'll use the white color to denote the four spectral components of the original cosine and sine signals. The real valued cosine signal consists of a complex sinusoidal signal with frequency at omega 1 and minus omega 1 and an amplitude of half. And the sinusoidal signal at frequency omega 2 also consists of two complex sinusoidal signals with frequencies omega 2 and minus omega 2. When the cosine and sine signal are multiplied together, we still have four spectral components. There's a spectral component at plus minus omega 1 plus omega 2, and another spectral component at plus minus omega 1 minus omega 2. The amplitudes of the new spectral components for the multiplied signal are 1 over 4i. These new frequencies are shifted up and down in frequency, and that's where the name up conversion and down conversion comes from.